Hello, and thank you for attending my presentation. I'd also like to thank the conference committee for organizing this event and allowing me the opportunity to present our research. My name is Dan. I'm a physics graduate student at the University of Rochester, and today I'll be discussing evolutionary computation as applied to optical physics. Specifically, we're interested in evolving the tuning parameters of deformable mirror in order to generate light fields that are partially coherent in space. In what follows, I will elaborate on this property of light and discuss its importance in more detail. So nonlinear optics concerns the propagation of intense coherent light fields through media, whereas the domain of statistical optics largely focuses on random weak fields. The combination of the two regimes of intense random fields appears in multiple contexts, such as in atmospheric turbulence, refraction of light in the sea, and laser amplification. Partially coherent light may also prove useful in applications such as laser machining, random number generation, and communication via high bandwidth multimode optical fibers, to name a few. So let's review the property of coherence. If we consider a monochromatic, linearly polarized laser electric field, it's written here as the product of a slowly evolving envelope function, A of RZ, and a complex exponential representing the carrier wave oscillation, plus their complex conjugate. So there are two types of coherence, and they relate to the phase of the complex valued electric field. When 2 points in space or 2 points in time exhibit a fixed phase relationship, then they are said to be coherent in space or coherent in time, respectively. Temporal coherence, which is illustrated diagrammatically on the right here, is shown by these waves oscillating in a synchronized fashion. In our investigation, we're interested in generating an ensemble of phase screens phi comprised of 1,000 to 10,000 members that are partially coherent in space. So there are a variety of methods to generate partially coherent light. Experimentally, one can use glass diffusers, which produces light with Gaussian phase statistics. Additionally, one can use a spatial light modulator or deformable mirror, depending on power and resolution constraints. Numerically, partially coherent phase screens can be generated via Fourier domain filtering correlation matrix methods such as the Cholesky and singular value decompositions and iterative Fourier-based analyses which operate in the simulation loop. It's important to note that in both situations, we seek to control both the two-point correlations and the single-point probability distributions. And I will elaborate on this point in more detail in the results section. So here we have a schematic diagram of the experimental setup that we will be using in the near future to study partially coherent light and to verify the phase distribution statistics generated numerically. So as illustrated, light from a CW or continuous wave laser first passes through a spatial filter and beam expander, after which it encounters a 50-50 beam splitter, which reflects part of the field to a deformable mirror, which is then transmitted through and focused onto a CCD camera. Beneath the surface of a deformable mirror are tunable actuators, which, as the name suggests, deform the surface to impart a position-dependent phase shift upon a reflected beam. So this is illustrated by the figure on the right, which shows an array of actuators tuned to different displacement or phase shift value settings. And in what follows by phase screen, I will mean a specific configuration of the deformable mirror actuators. And so the evolutionary calculation will provide sets of realizations of the deformable mirror matrix. And for each realization, the CCD camera will image the beam around the Fourier plane of the focusing lens, from which we can analyze the beam quality factor and verify these statistics. Now we'll discuss the numerical generation of phase screen ensembles. This flowchart illustrates a single iteration in the evolutionary calculation. The first step is to define the physical parameters of interest, and these include quantities such as the coherence length, the deformable mirror size, and the number of actuators, and so on. The goal is to generate phase screens whose values are statistically correlated in a user-defined way, approaching a target covariance function, which we define at the outset. So as will be discussed momentarily in the results section, this can be accomplished by evolving the phase values directly, or as illustrated in this diagram, evolving a function which generates an ensemble of correlated phase screens. In both cases, the objective is to minimize the root mean square error, or RMSE, between the evolving quantity and the target covariance function. So to perform the calculation, we use the Library for Evolutionary Algorithms in Python, also known as LEAP. It is a general purpose toolkit for evolutionary algorithms aimed at engineers, educators, and researchers, and it is developed and actively maintained by Dr. Mark Coletti of Oak Ridge National Laboratory and my co-author on this work, Dr. Eric Scott of the MITRE Corporation. The animation to the right is a demo of LEAP showing its generational evolutionary algorithm successfully minimizing an integer version of the Langermann function. So for further information, I refer you to the 2020 GECCO paper on LEAP, or you can find it on GitHub. So now I will share our results. First, let's consider brute force generation of phase values. In this case, the deformable mirror is comprised of 6x6 actuators, and we seek 1,000 such realizations that are correlated. That is to say, we are evolving phase values such that the ensemble average of their exponentiated difference between two spatial points approaches a target field covariance function, QF, as shown here by equation 1. So as mentioned earlier, the objective is to minimize the RMSE between these two quantities as the set of phase matrices phi evolves. Now, there are two covariance functions to have in mind. There's the field QF and the phase QP covariance function, and they're related by an exponential as shown to the right here. In this preliminary work, we consider almost exclusively a phase covariance function that is Gaussian in the 2-point separation, R2 minus R1. And here sigma is the standard deviation of phase values at a single point, and rho c is the correlation length, both of which we parametrically set equal to 1. The first figure here on the left is the target covariance function, and the result of brute force generation is on the right. And as you can see, the agreement is quite good. The evolutionary calculation converged quite successfully. Now, in discrete space, both quantities are four-dimensional arrays as they are dependent on the two-dimensional position vectors R1 and R2. But for the sake of visualization, we unwrap them into matrices as shown. The axes enumerate the unwrapped position vectors, and along the main diagonal, the covariance is identically 1, which trivially signifies that a point is completely correlated with itself. And moving away from the main diagonal, the band structure decreases in amplitude as a Gaussian fall-off. In the second figure, we have arbitrarily chosen a pixel on the 6x6 mirror and created a histogram of phase values based on the 1,000 ensemble members. Interestingly enough, the genetic algorithm converged upon a solution with a bias for phase values near plus or minus pi after having been initialized uniformly within this interval and evolved for 500,000 generations. Lastly, here's a record of the calculation's progress over time. Vertical axis is the RMSE, which characterizes the fitness, and the horizontal axis is time as measured in generations. And you can see that progress is quite slow up until about the 10,000th generation. And this may be due to less than ideal initial guess or evolution and mutation settings, which we did not optimize in this study. This calculation was performed for 10 trials. What's plotted here is the average and spread over trials, but in this case, the spread is so narrow, it's actually thinner than the width of the curve being plotted. And the evolution time was clocked at 61 milliseconds per core per generation. So for a 12-core processor, it took about 100 hours. In this next case, we're evolving a linear transformation that correlates phase values in the desired manner. So the objective is to find a matrix L such that LL transpose equals the phase covariance function QP. This approach is motivated by the Cholesky and singular value decompositions in which a similar procedure may be employed. That is, once such a matrix L has been found, then given a random normal vector Z, a single phase screen realization can be created just by multiplying LZ. And so if this is performed for an ensemble of, say, 1,000 such Z's, the generated phi's will be spatially correlated according to the field covariance function. In this case, we constrained L to be a lower triangular matrix in the evolutionary calculation. The final matrix is illustrated in the first panel here. The middle panel shows the residual between LL transpose and QP, and similarly, the right panel shows that between the ensemble average of e to the I delta phi and QF, both of which have relatively small maxima, indicating good agreement. The next figure shows the single point phase distribution, which in this case is Gaussian due to the generating random normal z vectors. In the near future, we hope to develop a method of controlling the first order single point phase statistics. Lastly, the evolution record for this case is provided in the rightmost plot. The variation in RMSE over 10 trials is more apparent here, and the calculation is an order of magnitude faster than the brute force approach. But in addition to being computationally faster, this method offers the advantage of allowing one to generate an arbitrary number of phase screens once a good L matrix has been found, just by increasing the number of z vectors employed thereafter. So in contrast, for the brute force approach, one would have to rerun the entire calculation and for a longer period of time, just to go from, say, 1,000 to 10,000 ensemble members. So as a step toward controlling the single point phase distribution, which may rely on symbolic evolution of correlating functions, we considered a soft symbolic approach to generating correlated phase screens. In this case, we defined a linear transformation whose column vectors are themselves Gaussian. Each column vector is defined by 5 evolving quantities highlighted here in red. They are the amplitude, the centers, and the standard deviations in both directions. The L matrix is therefore uniquely defined by 5 nx and y evolving quantities in total. And as in the previous case, the objective is to minimize the RMSE between LL transpose and QP. Once again, we show here the final L matrix and the residuals involving QP and QF. The upper panel shows the unwrapped Gaussian column vectors that constitute the cell matrix. And based on the small residual values, the agreement in this case is also quite good. Generating phase screens proceeds identically as before by multiplying L with random normal z vectors. And here is the evolution record for 10 trials. Now let's consider a super Gaussian covariance function where the order of the exponent is 4. As discussed in the appendix of our paper, according to physics theory, such phase statistics are unphysical. In other words, they cannot be produced in the real world in a laboratory under any circumstances. And this is related to the notion mathematically of positive definiteness of a matrix. In this case, the non-negativity requirement is of a quantity known as the cross-spectral density, which we have calculated and plotted here. And as you can see, the orange curve for a super Gaussian is just negative for a specific range of spatial frequencies. So to verify this theory, we tasked the genetic algorithm with finding a matrix satisfying the objective LL transpose equals QP, where QP is now the supposedly unphysical super Gaussian covariance function. After 10 trials, each employing 500,000 generations, we found that convergence was unsuccessful, and so the theory has been validated. As shown in the figures below, the phase and field covariance residuals are unacceptably large. And to the right below is the evolution record. You can see convergence to what we believe is the nearest realizable covariance function happens after about 10 to the 4 generations. An open question for consideration is whether this non-negativity condition can be used to limit the evolution search space. In this figure, we plot the fitness time evolution record for all cases just presented. As you can see, the red curve for the unphysical super Gaussian plateaus to an unacceptably large value. And furthermore, comparing the orange and green curves based on linear transformations to the blue curve, which is the brute force approach, we see that they evolve more gradually, but as noted earlier, their associated compute times are an order of magnitude faster. So in conclusion, we have demonstrated how evolutionary computation can be applied to generate partially coherent phase screens, and we've accomplished this in 2 primary ways, brute force and evolution of symbolic linear transformations. We have demonstrated control of the second order statistics, the covariance, but not of the first order statistics, which is the single point distribution. And in the near future, we will explore the possibility of using nonlinear transforms for first and second order control, consider simulating laser field propagation in the evolutionary computation loop, and conduct laboratory experiments using the generated phase screens. So thank you for listening, and please let me know if you have any questions.